Hey everyone, in this video we're going to go over section 3.7, Rates of Change in the Natural and Social Sciences. In this section we're going to discuss how the concept of a derivative naturally arises in the fields of physics, economics, and electrical engineering. So to begin, we'll talk about physics. So first off, let's recall that the velocity of some particle in motion is given by the derivative of its position, or that is, the change in a particle's position is equal to its velocity. Similarly, the acceleration of a particle as a function of time is equal to the change in velocity with respect to time. We can combine these two rows, and that says that the second derivative, or the change of the change in our position, is equal to our acceleration. So for example 1, Example 1 says the position of a particle is given by the equation, so position of particle is given by S of t being equal to t cubed minus 6t squared plus 9t, excuse me, where t is in seconds and s is in meters. Okay, so this gives us our position. And by position, you can think of it as our displacement. From one position, from where we start, it tells how far away we've gone. All it says is it's moved in one direction a certain amount. It can start to move back, and it would actually trace its path back along the same route, and it then could go forward again. This is really going on in one dimension. If we were to kind of accordion this up, it's possible for a particle to double back, and we're going to see that happens in this to this particle. But I wanted to say that off the bat. So this, though it is position, you can think of it more as displacement. And we want to do some stuff to, we want to analyze or get as much information about this particle as we can, or say as that particle, as we can from this equation. So I'm going to rewrite this on the back. So our equation, S of t, is equal to t cubed minus 6t squared plus 9t. And we want to do about 9 things to this. So I'm going to write them out. The first thing we want to do is find the velocity at time t. The second thing is we want to find the velocity after 2 and 4 seconds. Okay. Then C, we want to figure out when is the particle at rest. The fourth thing is when is the particle moving forward. And then we'll figure out when it's going backwards in that one too. And then we will draw a diagram to represent the motion of the particle. We're going to draw a diagram to represent the motion of the particle. F, we're we're going to find the total distance traveled in the first 5 seconds. In the first 5 seconds. Find the total distance traveled, of the particle during the first 5 seconds. Perfect. Find the acceleration at time t. That's the word the. And, more specifically, when t is equal to 4, h, and after h we'll do I, and that's it. Graph the position, velocity, and acceleration. With 0 less than or equal to t less than or equal to 5. And finally, we will discuss when is the particle speeding up. Perfect. So these are the 3, 6, 9 things we're going to do. I wanted to get them all labeled for you so you could skip ahead in the video if you need to for your homework. So we will get started. So the first thing we want to do is find the velocity at time t. So if our position or our displacement is t cubed minus 6t squared plus 9t, well, our velocity is the derivative of our displacement. By our power rule, the power comes down, we get 3t squared minus 12t plus 9. So, here's our velocity as a function of time. B was figure out what the velocity of the particle is at 2 seconds and the velocity of the particle at 4 seconds. Well, at 2 seconds, we'd get 3 times 2 squared minus 12 times 2 plus 9. 2 times 2 is 4, 3 times 4 is 12, take away 24 is negative 12, plus 9 is equal to negative 3. And if position is if your displacement is measured in meters, t is measured in seconds, then the unit on our velocity is going to be meters per second. Similarly for 4, we get 3 times 4 squared minus 12 times 4 plus 9. Oh, that's going to be 3 times 16 minus 48 plus 9. 3 times 16 is 48. 48, take away 48 plus 9 is just 9 meters per second. So, notice how we've got a negative and a positive velocity. We'll come back to that in a moment. So, we'll do C as well. C was, when was the particle at rest? Well, our particle is at rest when its velocity is equal to 0. That means we want to know when our velocity, 3t squared minus 12t plus 9, is equal to 0. You can divide a 3 from both sides and get t squared minus 4t plus 3 is equal to 0. That would factor to t minus 1 times t minus 3 is equal to 0, or t equals 1, or t is equal to 3. So, after the particle starts to move, 1 second later it stops. For whatever reason, its velocity goes to 0. and then its velocity is something other than 0 for a while, for 2 seconds. And then 3 seconds after the particle has started moving, it stops. For whatever reason, its velocity goes to 0. So what D is asking us, D is asking when is the particle moving forward? Oops. Well, when is the particle moving forward is asking when is the velocity positive. When we have a positive velocity, we're moving forward. We are traveling away from the point that we started. But I want to be careful in saying that we are traveling away from the point we are started. You have to pick kind of some start point. And so if you start moving with a positive velocity, for example, you could start moving this way. And if your velocity goes negative, well, that means you would start moving the other way. If you continue past the point that you start, you still have a negative velocity, though you're getting further away. So I don't want to call it further away or closer. I want you to think of it as moving in a positive direction or a negative direction. So when you have velocity being greater than 0, you're moving in a positive direction. You can move back and forth. You could start walking and you could pace back and forth. Every time you go back, your velocity is going to be negative and positive and negative and positive. We'll have to get some more information about this particle to know when it's moving, behind where it started. But by velocity being a positive number or a negative number, that's indicating a direction of motion. And there's nothing sacred about what direction is forward and what direction is negative. You just have to pick one. So, positive velocity moves in some positive direction. Negative velocity means you're moving in the opposite direction. So when is our particle moving forward? That means we want to take the velocity and we want to figure out when it's positive. That means, this is going to be D continued, we want to figure out when, velocity was 3t squared minus 12t plus 9 is bigger than 0. We can factor out a 3, and we know the left-hand side will factor to t minus 1 times t minus 3 being greater than 0. And this is a parabola. Just by looking at it, we know it's a parabola. It crosses the x-axis when, I should call it the t-axis. Crosses the t-axis when t is equal to 1 and when t is equal to 3. It has a positive orientation, so we know it goes up like that and up like that. So we can see graphically that we know that, and this is our velocity as a function of time, we see that velocity as a function of time is positive when we're over here, anywhere from 0 off to 1. We put a closed bracket on 0, because if we plug 0 into this equation, we get a positive 9 out. We know we're positive at the end point. Graphically, we know we're positive all the way to here. We don't put a bracket on 1 because we're neither positive nor negative at that point. We're 0. 0 is neither positive nor negative. It's just 0. And I should say t, when t is in that interval, or when t is bigger than 3. So we've got anywhere from the time we start to just before 1 second, we have a positive velocity, and for any time greater than 3, we have a positive velocity. Okay, so for part E, we're supposed to draw a diagram of the motion of the particle. So the particle is going to start, and this is going to be the s-axis, the displacement. So, and what we're doing is we're graphing the velocity. The velocity is going to increase to a point, then it'll decrease, and then it'll increase again. So this is an idea about the way the particle is moving. It moves forwards, then it moves backwards for a while, and then it finally starts to move forwards again. So for part F, if we wanted to find the total distance traveled by the particle, traveled over 5 seconds, we are actually going to have to split up our position function, which I have lost if you'll give me a second. We have s of t being equal to t cubed minus 6t squared plus 9t. Perfect. So what we want to do is, first off, we want to figure out how far the particle traveled during the first second. And so this will represent the distance traveled over the first second. Distance is always positive, so whatever sign that is, I want the absolute value of it. To that, now we traveled backwards from 3 seconds to 1 second. I want to add s of 3 minus s of 1. And finally, we want to add s of 5 minus s of 3. We want to figure out how far it traveled over that time interval, how far it traveled over that time interval, and how far it traveled over that time interval. The reason why we're taking absolute values is because we want the total distance, and distance is always positive. Okay, so let's go through and calculate these values. The value for this absolute value, well, we'll just do this. S of 1 minus s of 0, that's equal to 1 cubed minus 6 times 1 plus 9 times 1 minus 0 cubed minus 6 times 0 squared, I forgot a squared there, plus 9 times 0. This whole final term is 0. This will be equal to 1 minus 6 plus 9, which is equal to 2. So we get this value to be 2. Then we want to add s of 3 minus s of 1. Well, we know what s of 1 is. It's right here. S of 1 is equal to 2. So all I need to do is calculate s of 3. S of 3, and we'll say absolute value of s of 3 minus s of 1 is equal to, we'd get 3 cubed minus 6 times 3 squared plus 9 times 3 minus 2. All in absolute values. And I didn't have my absolute values here, and I should have. Equal to the absolute value of 2, which is equal to positive 2. So this will be equal to absolute value of 3 times 3 times 3 is 27, 9 times 6 is 54, plus 27, 9, 18, 27, minus 2 in absolute value. 27 and 27 is 54. Take away 54 is 0, and we get the absolute value of negative 2, which is equal to a positive 2 again. Finally, we need to calculate s of 5. We have already figured out that s of 3, this part right here, equaled 0. So on the back side, we know that s of 3 is equal to 0. S of 5 is going to be 5 cubed minus 6 times 5 squared plus 9 times 5. 5 cubed, if you have 5 quarters in your pocket, you've got $1.25. Minus 6 times 25, if you got 6 quarters in your pocket, you've got $1.50. Plus 45 is equal to negative 25 plus 45, which equals 20. My pen is about to die. It's getting scratchy. I'll only use this pen. Sure, I won't use that pen at all. So we get the absolute value of S1 from 0, the distance traveled from 1 second back to the beginning was 2, plus, now the distance traveled between 1 second and 3 seconds, it actually went backwards 2, but the total distance was 2. And then in the last 2 seconds from S3 to S5, it went a total of 20 meters. So in total, the particle traveled 24 meters over the first 5 seconds. There was a mistake in that. I wonder if you guys caught it. 1 take away 6 plus 9 isn't 2. It's definitely 4. The absolute value of 4 is 4. Now, that means S of 1 is equal to 4. So when we do S of 3 minus S of 1, it would be S of 3 minus S of 1. S of 1, that still equals 0, so we get negative 4, which turns into a positive 4. So on the back side, that one was correct. We actually get 4 plus 4 plus 20, which equals 28 meters over the first 5 seconds. Sorry about that. Got excited. Okay, so the next thing we're going to do is we're going to find the acceleration at time t and the acceleration when t is equal to 4. So we have to take our function, and this is g. We'll take our function, d cubed minus 6t squared plus 9t, and let me double check that, minus 6t squared plus 9t. We take our first derivative, it gives us our velocity, 3t squared minus 12t plus 9. Then we take our second derivative, 6t minus 12. So this is the function that gives the acceleration of the particle for any set time. So when t is equal to 5, a of 5 is equal to 30 minus 12, which is 18 meters per second squared. Since we took another derivative, we divided by t again. That's why we have a meters per second squared. So let's see, 6t minus 12. Oh, yes, I'm sorry. I was looking at the wrong spot. So that is the acceleration. We wanted acceleration when time is equal to 4. I looked at the wrong directions. Well, acceleration when equal to 5. Acceleration when equal to 4. 6, 12, 24. 12 meters per second squared again. Okay, so the last two things we're going to do is we're going to graph the position, velocity, and acceleration for this particle as a function of time, and we're going to discuss when the particle is speeding up. I'm going to do both of those on my computer.
So what I have here is I have the graphs of the position, the velocity, and the acceleration functions. And I know it says x, but this is for all time values between 0 and 5. So part I is when is the particle speeding up? So the particle is speeding up when its acceleration and its velocity have the same sign. So for instance, not that one, over this time interval, and the blue line is the velocity and the green line is the acceleration. The blue line says that the particle is moving forward, and what the green line says is that there is a force pushing on it in the forward direction. Now you can speed up backwards too. What this line says down here, now our velocity is negative and our acceleration is negative. That means we are speeding up, but in the backwards direction. So we can speed up forwards and we can speed up backwards. You speed up forwards when your velocity and acceleration are positive, and you speed up in the backwards direction when your velocity and your acceleration are negative.
So we'll move on to our second example. Example 2 is dealing with economics. So, in the field of economics, businesses care about how much it costs to produce a specific item. Businesses will often care about their cost function. Their cost function as a function of x. This is how much it costs to produce that many. So our cost function, how much is it going to cost some fictional business to produce that many? So cost functions, they can come in all sorts of forms. A lot of times they'll come in the form of polynomials, such as 10,000 plus 5x plus 0.01x squared. So this first value, it's a constant term. Regardless of how many items this company produces, it's going to cost them $10,000. This often gets thought of as, how much it costs to turn the lights on, how much, that's kind of what your overhead cost is, the things that don't necessarily relate to the production of your item, but also wind up costing the company business. Not costing the company business, costing the company money. And now, we've got these different powers of x depending on how many items get produced. That should make sense because different things impact the cost to a company differently. The cost of buying new materials might increase linearly. The more materials you have to buy, the more you have to pay for your materials. But if you consider overtime hours, when employees start to get paid 1.5 times or double time or whatever it is with that company. So different things could impact the cost of the company or impact the cost of producing a certain number of items. So what businesses are also concerned with is they're interested in the change in the cost per the item. They want to know how much is the cost, how much is the change in how much it's costing a company, how much is the cost of producing items changing with regards to the number of items produced. That's a better way of saying that. How much is the cost of production changing with respect to the number of items produced? So, for any 2 points you could get a secant line, but what we've been doing is we've been taking limits as delta x goes to 0, and this gets called just the marginal cost. C prime of x is called the marginal. It's called the marginal cost. This gets analyzed as how much the cost is changing at a specific moment, or how much would it cost to produce one more item. A lot of times, companies are going to try and make sure that their marginal costs are going down. You want to have the cost of what you're doing go down. If the cost is just increasing, then you wind up spending more and more money. But marginal cost, the big takeaway is you will need this for your homework. The derivative of a cost function is a marginal cost. So let's, working with this example, if c of x is equal to 10,000 plus 5x plus 0.01 x squared. So first, let's see how much it costs to produce 500 items. If the company wants to produce 500 items, that's going to cost them the $10,000 it costs to turn on the lights, plus 5 times 500, plus 0.01 times 500, 500 squared. That's going to be equal to 10,000, plus, that's a 25 with 2 zeros, plus 0.01 times 25 with 4 zeros. It's going to be equal to 10,000 plus 2,500 plus, and that's going to move a decimal, 1, 2 right there, plus 2,500 again. That's 10,000 plus 5,000, which is $15,000, assuming that we're working with dollars, 15,000 Monopoly monies. But how much is that cost changing? What is the marginal cost? Well, the marginal cost, the derivative of a cost function, derivative of a constant is 0, derivative of 5x is equal to 5, plus by our power rule, this becomes 0.02x. And now the marginal cost is going to be 5 plus 0.02 times 500, which is going to be 5 plus, that would move it over 2, that would cancel out with that, 2 times 5 is 10, and we get $15. But now let's think of the units. This is just $15,000, and when we divide by delta x, remember delta x is the quantity produced, so this would give us dollars per unit. That's saying that when we're making 500 units, it's going to cost approximately $15 more to produce your next unit. So that's largely the idea of marginal cost in economics. Our final example is just a concept. So if we have a wire, or a tube or something that we send electrons through, and these are going to be our electrons. That's a minus sign, they flow that way. These are electrons. So if we call, let's call delta Q the net charge, the net change, or the net charge of electrons that pass through a plane. Delta Q is the net charge of electrons that pass through a plane. So if delta Q is the net charge of electrons that pass through a plane, we'll say over some time delta T. Well, so what we're doing is, at this point, we're saying, okay, these electrons are flowing. So over the course of time, the electrons that are going to pass through this plane, well, all of these are going to pass through. It's almost like we're counting the total electrons over a certain region. And now, what's actually defined as the current denoted by a capital I is equal to the limit as delta T goes to 0 of that net charge divided by the change in time. Or going back to thinking of it this way, that's like saying, well, as we shrink time, as that interval of time gets smaller and smaller, well then the total number of electrons that are going to pass through this plane are going to shrink. And what we wind up doing is we wind up calculating how many electrons go through this flat two-dimensional plane inside of this three-dimensional wire. This unit of charge is often called an ampere. A-M-P-E-R-E-S. And it's a measure of current. It's a measure of flow. Other examples of rates of change include power. Power is the rate at which work gets done. The rate of heat flow. If you have another piece of paper, if you just have some lump kind of sitting there and it's radiating heat, the rate at which this thing radiates heat is going to be, you're going to have a derivative floating around, I'll say that. You can talk about the temperature gradient of this item across its surface. If it was heated from a specific point, how that heat is radiating out is another example of derivatives. A lot can be said about a vibrating string based off of information about its derivative. And as we'll see in the next section, if we have some radioactive isotope, the rate at which that isotope decays, or the rate at which it loses mass, is going to have a derivative. Whenever we have rates of change floating around, if you hear rates of change, think of derivatives. Even if you find yourself in one of your future classes and you're not explicitly given a function to take the derivative of, rates of change get modeled by derivatives. So for homework, go off and do 7, 9, 13, 15, 19, 31, and 35. What I would also encourage you to do is just read 3.7, that section that I just lectured over. Go through and read this section in its entirety. There's not a lot of doing calculus, and to spare you guys having to sit through a story time, I did not read the entire section to you. I gave you the bits that you'll need for your homework, but like I said, I would encourage you to go through and read this section in its entirety to see if any of the examples in the section pertain to what you want to do after college, what you want to be when you grow up. So yeah, go and do those, and let me know if you have any questions. Have a nice day.